There's a logical sequence that helps students understand formulas and build their knowledge as we go. If we start with perimeter first, it helps because it's the most basic of the formulas and it's easy to see. The distance around something is easy for students to understand. Once they understand that clearly, then we can move to area. When we teach area, we want students to understand that area means that we are covering a space. We are covering the inside of a shape. For the area of a square, for example, we're taking a smaller shape, something that's a square unit. It could be a square centimeter, it could be a square inch, in some cases it could be a square foot, but we're taking a square unit that we identify, and we're figuring out how many of those square units it would take to cover a given shape. So if we're trying to find the area of this square, we would maybe start by saying, well, we can get 4 of these units in a row. And now we need to know how many of those rows would we need to have to absolutely cover the shape. So we would add another row, we would add another row, and we would add another row. And it's very important for students to actually do this, to actually cut squares, cover the shape, and have them know that area is covering. When I walk into classrooms and I ask students what area is, they will often tell me it's base times height or it's length times width. That's not what area is. That's how we find area. But what area is means we're covering a shape completely with units that are the same size. So in this case, if students actually did this, they could count up the units and see that there are 16 square units in this shape. That's the area because it takes 16 units to cover it, and those units are square. It's very logical, and we want students to see that. After they've worked with squares a bit, then we can move to the idea that, okay, there are 4 in each row, and there are 4 rows. So what we're doing is we're taking one length of the side, which is 4, and we're taking it times itself to get the area of a square. We're taking the length times the width, because one of those numbers tells us how many squares there are in a row, and the other one of those numbers tells us how many of the rows there are. So in this case, the formula for finding the area of a square is area equals side squared, or the side times itself. The logic in finding the area of a rectangle is exactly the same. So if students understand how to find the area of a square, they can just transfer that very easily. So if we're finding the area of a rectangle, we're doing the same thing. We're taking a unit and we're trying to figure out how many of those it would take to cross a row, to go across. And then we're figuring out how many of those rows there are. So if this rectangle is 8 inches here, and if it is 4 inches here, that means we can get 8 squares across, and if we make 4 rows, there are going to be 8 in each of those rows. So again, students could count these up and see that there are 32, or they can just say 8 across times 4 rows of 8 will give us 32. And our answer then is 32 inches squared. Why inches squared? Because we're finding area by covering something with a square that's 1 inch on each side. We want that to be very logical so that they can picture what a square inch looks like. So what is the area of a rectangle then? We have length times width, or sometimes base times height. We want to make sure that students can understand why that formula works. What is it they're actually doing when they use that formula? When students understand how to find the area of a square and what area is, and then they understand how to find the area of a rectangle, it's very easy to move to finding the area of a parallelogram. The area of a parallelogram is found in the same way. It's length times width, or base times height. Why is that? Well, we want students to understand that if we took this parallelogram and we kind of gave it a big push here and we made it move so that it was straight, we would still just have a rectangle. We can also make them understand this by saying, what if we cut this piece off right here and we move it over here and we put it upside down, now our shape looks like this. We haven't changed the size at all. We've just taken this piece and moved it over here. It's exactly the same. So now that we have a rectangle, we can find the area the same way we did with a rectangle. We have length times width, or base times height. We need to make sure that students understand at this point that height is a measure that will be at right angles to the base. Sometimes students will misunderstand, and they might think that this line represents the height, or this line represents the height. So by taking this piece and moving it over here, we make it very clear that the height has to be a measure that is at right angles to the base, and that they can use knowledge that they already have in a new situation by making slight changes in what they're doing that don't change the actual size or the area of the figure they're working with. Students are always building their knowledge when it comes to formulas. So if they understand completely how to find the area of a rectangle, they can use that information to find the area of a triangle. And when we start with the area of a triangle, it's typically easier for students to see the meaning of the formula if we start with a right triangle like this one. So if we're trying to find the area of this triangle, we can say, well, this triangle is half of the rectangle we could make if we used these two sides to create that rectangle. And we know how to find the area of a rectangle. So area of a rectangle is length times width, or base times height. That's how we find the area. This triangle takes up half of that space. So if we take the length times width over 2, divide it by 2, that will give us the area of a triangle. So triangle equals 1/2 of the base times height, or length times width, whichever terms you choose to use. Why is that? They can see it. It's logical. When we have a triangle like this one, it can be a little more difficult for students to see it, but we can show them. And sometimes a nice way to do this is by using paper figures or plastic shapes so they could actually play around with it. So here's a triangle. We're going to build a rectangle that has the same size as the base. And we're going to try to prove that this triangle takes up half of that space. So again, if we were to allow students to cut the triangle in half, they would see that this and this are the same, and this are the same. So if I do this in this way, I have 4 pieces in my rectangle. 2 of those pieces are used to make this triangle. So the triangle is actually taking up 1/2 of the space. So the formula still works. It's important to have students work with a variety of triangles, different shapes, triangles that are equilateral, triangles that are isosceles, triangles that are scalene, all different kinds of triangles so that they can prove in their own minds that this formula will work no matter what. This is, again, just a rule of nature. This is how triangles are. They take up half the space of their relative rectangle or square. The idea of building on what we already know is so important in math. It saves us work, it saves us complicated thinking, it helps us to apply old information in new situations. And the area of a trapezoid is an example of that. As we find the area of a trapezoid, we have kind of a dilemma here because we don't have a rectangle, we don't have a square. We could cut it up and we could find the area perhaps of each little part. This, we know how to do that. We know how to find the area of a triangle. So it's possible we could do that. But each one of those will be different, and when we use a formula, we want something that will generalize it. So here's something that's kind of interesting. If we take this trapezoid and we copy it exactly, but we flip it upside down so that it looks something like this. Now my drawing isn't exactly the same, but we have a trapezoid here. We have the same trapezoid here, and with students you could do this with cutout shapes or with plastic shapes, and they could see that these two are exactly the same except that this one is flipped, it's upside down. By adding this one to our original trapezoid, we now have a parallelogram. Here's our parallelogram. And we already know how to find the area of a parallelogram. We know that the area of a parallelogram is base times height. So we can use what we already know to find this new area. There is a problem. We now have twice the space that we started with. We want to know what the area is of only this trapezoid, and we've made our shape bigger. So once we find the area of this larger parallelogram, we're going to have to cut it in half because we only want half of the area. We only want the shape we originally started with. So that means that the formula for finding the area of a trapezoid is base 1 plus base 2 times the height divided by 2. Now let's look at what we just did. We took base 1, let's say that the bottom of this is base 1, plus base 2, that's actually up here, but we're adding it because we added it here. So those two together, base 1 and base 2, give us our new base. Now if we take that times the height, that will then give us the area of that parallelogram. But we only want half of it, so we divide it by 2 to get only half. It's really very logical when you see it, and it's sort of a trick. It's sort of magic. It's sort of a shortcut. Students can use something they already know to find something that's a little more complicated, and they like that. On the video about perimeter and circumference and finding that and learning about formulas, I mentioned that those are good ways to teach students what a formula is for and why it works. When we talk about finding the area of a circle and the formula for that, it's almost the opposite. This is kind of a nice time to have students start with the formula and then think backwards to why this formula would work for them. So the area of a circle can be found with this formula, pi r squared. That equals the area of a circle. That's what we use. Why does that formula work? Let's just think about that for a minute. What is r in a circle? R is the radius. Now a radius could be anywhere, right? It could be anywhere from the center of the circle to the outside of the circle. So there we have a radius. What does radius squared then look like? It means that we're actually making a square out of the radius. We're taking the radius times itself. So what does that look like in a drawing? It means we're creating a square out of the radius. Each side of that square is the same length as the radius. So there we have radius squared. Now, if we look at this drawing, how would we find the area of the circle? Well, radius squared gives us this piece, although there's a problem because it kind of sticks out over here past the circle. But for right now, let's just let that go. Let's just say we copied that square and we made another one here, and we made another one here, and we made another one here. Now we have covered the circle, and we know that area means to cover something. How did we do that? We took r squared times 4. We have r squared, which is this square, and we have 4 of them. 1, 2, 3, 4. Now the problem is that what we've done here is find the area of the square that's outside the circle, not actually the area of the circle itself. So what would we need to do to find just the area of the circle? Let's think about that. Well, I think what we'd want to do is we'd want to chop off these corners. Let's get rid of that, let's get rid of that, let's get rid of that, let's get rid of that. If we could do that, we would now have just the area of the circle. Well, pi is the magic number that helps us do that. To find the area of the square, we took r squared times 4. So we know that if we're going to chop off these corners, it's got to be something a little less than 4. 4 is too big. Pi is that magic number that somebody has discovered that always works. Pi is 3.14. It's a little less than 4. It's the magic number that chops the corners of the square off for us so we can just have the area of the circle. So to find the area of the circle, we have radius squared. We make a square out of the radius, and we take it times pi because that gives us the area of these four sections without the corners. If you look on different websites, you'll find a variety of ways of showing why the formula for the area of a circle works. But to me, in my years of teaching, this one has helped students the most just to understand what that formula means and what it's doing. It works in kid language. It works by saying we're chopping off corners or we're doing things that they can actually see that's less mathematical and more visual. And I think at the elementary level, this really helps students understand. So when we're teaching area of any kind of a shape, a square, a rectangle, a parallelogram, a trapezoid, a circle, we want students to understand that we're covering that shape with square units. That's the basic foundation of what area means. And then we can carry our learning from one shape to another, from a square to a rectangle to a parallelogram to a trapezoid. In a circle, we're dealing with something a little bit different, but even there, we can use the information we already learned and apply it in a new situation.